Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1. We're given that x prime equals ax, and it has the general form for a solution. X is some constant e to the 2t 2, 3, plus some other constant e to the minus t 1, 3. And we're said to find the matrix A. So we have the solution. What's the problem? All right, so how do we do it? How can we find this? And I'll say there's a couple of different ways to do this. And so I'm going to go through and talk about, let's do it 2 ways. So here's the way I think is a fun way to do it. So let's lean into the fact that we have solutions. And so, all right, method 1. And what we're going to do is we're going to find e to the at. And the reason we can find e to the at is because we have the solutions. So we start by saying, well, we know what a fundamental matrix looks like. We populate it using the values, or rather the solutions, right? So the first column will be the first solution. 2e to the 2t and 3e to the 2t. And then the second solution will give us the second column. E to the minus t, 3e to the minus t. All right, good. Now, what can we do? Well, if we have a fundamental matrix, we can get e to the at. There's a nice little formula on our formula sheet. I happen to have a copy of it here. That says e to the at is phi of t, phi 0 inverse. So let's find phi 0 inverse. And first off, we should say, well, what is phi of 0? Just plugging in 0. Well, e to the 0 is 1, so it's just the coefficients. 2, 1, 3, 3. So the inverse of this, well, will be 1 over the determinant, 6 minus 3. So 1 over 3, swap the diagonals, 3, 2, change the signs on the off diagonals, minus 3, minus 1. And if you're ever in doubt, you can do some quick multiplication and just check. 6 minus 3 times a third is 1, minus 2 plus 2 is 0, 9 minus 9 is 0, minus 3 plus 6 is 3, but times that by a third is 1. All right, so with phi of t and phi of 0 inverse, what do we get? Well, we get that e to the at, that's equal to the product phi of t, phi 0 inverse. So that's 2e to the 2t, e to the minus t, 3e to the 2t, 3e to the minus t. Okay, now multiply that by this inverse, which is, there's a 1/3, 3 minus 1, minus 3, 2. Well, I'll leave the 1/3 out in front, and then we multiply through. So we're going to get a 6 e to the 2t minus 3 e to the minus t, and that's just the one entry there. Then we're going to get a minus 2 e to the 2t and a plus 2 e to the minus t. And then we're going to get a 9 e to the 2t and subtract 9 e to the minus t. Then we'll get a minus 3 e to the 2t and a plus 6 e to the minus t. Good. Now, at this point you're like, great, but why do this? Well, now comes the magic. If you take the derivative of e to the at, what happens? What's going to happen? Well, the derivative of e to the at is a e to the at. And now plug in t equals 0, and we get the following. Namely, if you take the derivative of e to the at and evaluate at t equals 0, well, you have a times e to the 0. And e to the 0 is identity, like the 1. So we get a. So we're like, what? That's cool. So here we go. We're going to take the derivative of e to the at. So we have our 1/3. That stays out in front. Then we're going to get 12 e to the 2t plus 3 e to the minus t minus 4 e to the 2t, right? We're taking the derivative entry by entry. Minus 2 e to the minus t, 18 e to the 2t plus 9 e to the minus t minus 6 e to the 2t and minus 6 e to the minus t. Now, plug in 0, and what do we get? Okay, so we're going to plug in t equals 0, and we get that a, right? Take the derivative, plug in 0. A is 1/3 times, and e to the 0 is always 1. So we have our 12 plus 3, our minus 4 minus 2, our 18 plus 9, and our minus 6 minus 6. Well, we can clean that up. 12 plus 3 is 15 times 1/3, 5. Minus 4 minus 2 is minus 6 times 1/3, minus 2. 18 plus 9, 27. Times that by 1/3, that's 9. Minus 6 minus 6 is minus 12. Times by 1/3, minus 4. And there we go. And there we go. There's our answer. Ta-da! Clean. Clean. All right. And that works. You can even check a few things. Like, hey, what are the eigenvalues? Well, they should be 2 and minus 1, right? So you can check, do these entries sum up to 1 on the diagonal? And if you take the derivative, do you end up with a minus 2? And in both cases, the answer is yes. So that's a really good sign. We got the right eigenvalues, and you can even check eigenvectors. But really, if we're going to go in that route, let's talk about method 2. Now, the first method leans into differential equation ideas. The second method says, let's lean into linear algebra ideas. So this method, I don't have a great name for it, but I'm going to say use eigenvalues and eigenvectors. So what do we have? Well, we have solutions, and so what we can do is we can extract information. So from our first solution, that would be e lambda t. So we have that lambda equals 2 is an eigenvalue, and the eigenvector is 2, 3. Then here, e minus t, that says lambda is minus 1 is an eigenvalue, and the eigenvector is 1, 3. And now, well, let's give our matrix A a name. A is A, B, C, D. And what do we know? Well, what we know is the following. let's start with the first eigenvector-eigenvalue pair. If we take A, B, C, D times the vector 2, 3, we're going to get what? We're going to get the eigenvalue 2 times the eigenvector 2, 3. Right? That's what the eigenvalue eigenvector refers to. It says, here's a really nice direction associated with this linear transformation, what a matrix represents. And so this gives us a pair of equations. 2a plus 3b has to equal 4, and 2c plus 3d has to equal 6. Now we're going to do the same thing with the other eigenvector pair. A, B, C, D times 1, 3. All right, well, that's the eigenvector. We're going to end up with negative 1 times 1, 3. So again, this gives us some equations. A plus 3b has to equal what? Minus 1. All right, so we're just looking at the top entries. And then if you look in the second entries, c plus 3d, what's that has to equal? Negative 3. And now we have two pairs of two equations with two unknowns. And so we just have to solve. But they were nice to us. And they said, hey, because we like our students, we'll make them clean. So for instance, if you subtract here, 2a subtract a, oh yeah, a, the b's disappear. 4 minus minus 1 makes 5. So a is 5. Similar, subtract here, what do we get? 2c minus c, the d's go away. 6 minus minus 3 makes 9. So a is 5, c is 9. Once you know a, plug it back in. 10 plus 3b equals 4, or 3b equals negative 6, or b is negative 2. All right, we know c, plug it back in. 2c makes 18, plus 3d equals 6. Or 3d, 6 subtract 18 is negative 12. Divide both sides by 3, negative 4. So there's our A, B, C, D. And what do? Well, those are the entries in the matrix we're looking for. And so we put them in. Ha-ha, ho-ho. So our matrix would be A is 5, B is minus 2, C is 9, and D is minus 4. And we're done. And if you look, we got the same thing, right? Coincidence? No. These are just two different methods to get to the answer. Are there other ways? Ah, yes. Do we need more ways? No, I think 2 is probably enough. But if you like to explore other ways to solve this, that's great, because there's lots of things you can do. All right, what a good start. Number 2, use a fundamental matrix approach to solve. We have an x prime is 4 minus 2, 2 minus 1x, with some initial conditions. X is 0 is 4 minus 1. Now, you'll notice here it says a fundamental matrix approach. And ultimately, when we're using a fundamental matrix with initial conditions, the way we do that is to say, there's a really good fundamental matrix that we like. So if we're doing a fundamental matrix approach with initial conditions, we say that our solution looks like e to the at times our initial condition x of 0, where this is our matrix A. So what's our plan? Our plan, find e to the at, multiply by 4 minus 1, life is good. Well, so where do we begin? The first thing we need to do is understand this matrix A. And in particular, we need to understand what can we say about the eigenvalues. So the eigenvalues, there's three possibilities: distinct, real, complex, and repeated. And depending upon which one we encounter, we'll do something slightly different. So we're going to take a second, maybe a minute or two, and start by saying, what are the eigenvalues of A? And with practice, you can almost start looking at them and reading off the eigenvalues, right? We know that they have to add to 3, and then that's the sum along the diagonal, and the determinant has to be 0, right? Because you have -4, and then we're going to subtract -4. So the eigenvalues are 3 and 0. But let's pretend we didn't see that. Let's go through the work. So determinant A minus lambda I. So that's the determinant. Put minus lambdas on our diagonals. And, okay, so they have 4 minus lambda, -1 minus lambda, subtract 2 times -2. So that makes a lambda squared. And then we have a -4 lambda and a plus lambda. So that's a -3 lambda. And then we have a -4 and a +4. They cancel. We say, oh, well, that factors pretty nicely. Lambda times lambda -3, which gets us to lambda is 0 and 3. All right. Well, so good. Good. Now we know our eigenvalues. They're distinct. They're distinct real eigenvalues, which means that we are going to go through and find eigenvectors. All right, so what are our eigenvectors? Well, we have two things to look at. For lambda equals 0, we're going to match, we come up here. Here's A minus lambda I. I'm going to put in lambda equals 0, and that gives us 4 minus 2, 2 minus 1. Multiply it by the eigenvector, we should get 0, 0. Now, the question, what vector does this? Well, if you can see it, great. If not, have a plan. Here's my plan. I pick a row. All right, now I'm going to write that row in reverse order and change one of the signs. So I claim 1, 2 does it. Well, you can always check. 4 minus 4, 0. 2 minus 2, 0. Nice. So, all right, good. So we have lambda equals 0, 1, 2. Now we'll do the same thing again, except for 3. Okay, so lambda equals 3. So think of it, we have our A minus lambda I, put in 3, and we get 1 minus 2, 2 minus 4, times something needs to give us 0, 0. Okay, well, what can we do? That first row, that looks pretty tempting. I like it. Let's use it. And we're going to just write that row, reverse order, flip a sign. 2, 1. Well, does it work? 2 minus 2, 0. 4 minus 4, 0. Yeah, it works. So for lambda equals 3, we're going to use 2, 1. All right, so there we go. All right, now, what does this tell us? Well, what this tells us is that these give us solutions. So the lambda equals 0, 1, 2, that says one solution is e to the 0 t, which e to the 0 is 1, times 1, 2. So I'll call my first solution is simply 1, 2. And then my second solution, well, that would look like what? E to the 3t times 2, 1. All right, good, good. So when we have distinct eigenvalues, distinct real eigenvalues. This is how we start. With our eigenvalues, eigenvectors, and two solutions set up, we're now able to put together a fundamental matrix. So we write it down. Our fundamental matrix, use these solutions as columns. So 1, 2, 2 e to the 3t, e to the 3t. Okay, x1, x2. I'll go ahead and mark that just so I can follow along later. x1, x2. Now, how do we get e to the at? That's where we want to get to. And the answer is we have, well, e to the at is phi of t, phi 0 inverse. So, what do we need to compute? We need to define phi 0 inverse. So let's figure that out. Phi 0 inverse. And, that is plugging in 0, and e to the 0 makes 1. 1, 2, 2, 1. Inverse. So that would be 1 over 1 subtract 4. That's negative 3. And flip the diagonals. 1, 1. Change the signs in the off diagonals. Minus 2, minus 2. All right. Now, we're ready. Here we go. Let's finish our problem up. We know that x is e to the at x of 0. But we know that e to the at is phi of t, phi of 0 inverse x of 0. So what we need to compute, we'll write these terms down, 1, 2, 2 e to the 3t, e to the 3t, times negative 1/3, 1 minus 2 minus 2, 1, times x of 0 is 4 minus 1. So, question, how do we go about multiplying? And here's the thing. We have two choices. We can either multiply the first and the second, or we can do the second and the third. And so either way works, right? Because we're going to go through 2 rounds. So here's the thing. As a mindset, if you were thinking in terms of efficiency, it's easier to multiply matrix times vector than to do matrix times matrix. And so I'm going to multiply matrix times vector, and then I'll have another round of matrix times vector. So it's a little bit easier to sort of multiply sort of in this direction, if you will. Okay, so that is to say that we are going to start over here. So let's do this multiplication. We're going to get 4 plus 2, also known as 6, minus 8, minus 1, also known as minus 9. Then there's this negative 1/3 that we can throw in front, and so this becomes a minus 2, 3, once we multiply that through. So, updating, we need to take 1, 2 for the first column, 2 e to the 3t, e to the 3t, second column, times negative 2, 3. Which gives us minus 2 plus 6 e to the 3t minus 4 plus 3 e to the 3t. And we're done. We're done. That's it. That gives us our solution. And it does everything that we need it to do. Now, on a side note, you can go ahead and just run through the computation. But you will see if you multiply these together first, and then you multiply by the 4 negative 1, you'll get the exact same answer, but it does get messier. So it pays to think about, hey, if I have a choice, which one will be the nice one? Because remember, we like ourselves, and we want to be kind to ourselves. We deserve it. We are good people. All right, let's keep moving right along. Number 3. We're asked to find e to the at, for a is minus 3, 7, minus 4, 8. All right, cool. So what do? When we're asked to find e to the at, well, the good news is we have plans. And in fact, if you look at the formula sheet, there's a nice set of formulas. And for this part of the course, there's just this single box here. This box is the formula sheet for this part of the course. And all of them deal with e to the at. So there's 3 formulas for e to the at, and they correspond to the 3 situations which we might encounter. So the first formula says e to the at is phi of t, phi 0 inverse. This is your go-to if you have distinct real eigenvalues. The second formula says e to the at is e to the lambda t, I plus t, a minus lambda I. This is your go-to if you have repeated real eigenvalues. So your eigenvalues look like lambda lambda. The last one says e to the at is e to the alpha t cosine beta t times I plus 1 over beta e to the alpha t sine beta t times a minus alpha I. That is your go-to if your eigenvalues are alpha plus minus beta I. So we have to decide which one of the 3 formulas to use, and that boils down to, hey, what's going on with your eigenvectors? So when you're asked to say find e to the at, the first thing you say is, what are the eigenvalues? Okay, so let's do our eigenvalues. All right, so we're taking our determinant of a minus lambda I, and so we have our minus 3 minus lambda, 7 minus 4, 8 minus lambda, and okay, minus 3 minus lambda, 8 minus lambda, subtract negative 4, 7, which will give us the lambda squared, that's the minus lambda times minus lambda. Then we'll have a plus 3 lambda minus 8 lambda, plus 3 minus 8 will give us a minus 5 lambda. Then we have a minus 24 and a plus 28. Minus 24 plus 28 gets us to a plus 4. All right, so there we go. And now, can we factor? Yeah, I think this one has a good chance, right? 2 things that multiply to 4 add to negative 5. I think minus 1 minus 4. So, or if you like lambda minus 1, lambda minus 4. Let's check. Lambda squared, that's good. Minus 4 lambda minus lambda is minus 5 lambda. And minus 1 times minus 4 is 4. All right, nice. And since we set this equal to 0, we get lambda equals 1, lambda equals 4. Distinct real. All right, so that's our setting. We're in distinct real. Okay, well, in that setting, we say, good, keep going. And when I say keep going, what I mean is, what is the eigenvectors associated with the eigenvalue for each one of the 2 eigenvalues? Well, so okay, let's do that. We start with lambda equals 1. And so come up in, here's your a minus lambda I. Put in lambda equals 1. You're going to get minus 4, 7 times something has to give us 0, 0. And the question is, what's the something that does that? Well, it's not too hard to figure it out. And if you're not sure, just grab a row. Well, it doesn't matter which row, they're identical in this case. Write the row in reverse order and flip a sign. So I claim 7, 4 does it. Minus 28 plus 28. Minus 28 plus 28. Yeah, 0, 0. And so we say, okay. That gives us a pair. Namely, lambda equals 1 goes with 7, 4. Okay, now on to our other eigenvalue. Lambda equals 4. Well, what is that going to do? So we come up here and put in 4. And okay, minus 3 minus 4, minus 7. 7. And then we have minus 4, 8 minus 4, 4. And something equals 0, 0. Now what can you do? Well, you can pick a row, or if you just see something, put it in. As long as it's not 0, you're good to go. And I claim 1, 1 works. Right? Let's check it out. Minus 7 plus 7. Minus 4 plus 4. Now you might say, I wouldn't have seen that. Well, what you could have said is like, okay, you probably would have said, I see this solution, right, which comes from reversing and then scaling. Flipping a sign. But now, say, look, you can always scale eigenvectors, but by something non-zero. So, if you end up with an eigenvector which has a common factor, scale it out. And so we can scale to get 1, 1. Okay, so that says for lambda equals 4, we get 1, 1 is an eigenvector. All right. Now, here's the thing. We are going to construct our e to the at using our formula. So from the formula sheet, we know that e to the at is phi of t times phi of 0 inverse. So we have to find phi of t, and then we just run it through. Now you might say, well, wait, there's no differential equation here. How do you find it? Well, the answer is you pretend like there's a differential equation. You say, oh, this phi of t, you think of it as this comes from x prime equals ax, right? That differential equation. And they say, oh, well, if that's where it's coming from, I know how to turn these into solutions. So we have that our two solutions look like x1, e to the 1t, 7, 4, and x2 would be e to the 4t, 1, 1. Now, our phi of t says each solution is a column. Excuse me, something in my throat. So we have 7 e to the t, 4 e to the t, and then we have e to the 4t, e to the 4t. And just as a reminder of where things are coming from, this is our x1, this is our x2. All right, we're in our home stretch. We have our formula. We have phi of t. Let's take a minute and do phi of 0. So, what is phi of 0? When you plug in 0, well, you just get the coefficient, 7, 4, 1, 1. Phi 0 inverse. All right, 1 over the determinant, 7 minus 4, 3. And then you swap the diagonal entries and change the signs in the off-diagonal entries. If you're concerned, carry out the multiplication. 7 minus 4 is 3 times a third is 0. Minus 7 plus 7 is 0. 4 minus 4 is 0. And minus 4 plus 7 is 3 times a third is 1. So we're now one computation away from being done. All right, so what's our last computation? We do the following. E to the AT is phi of t, 7e to the t, 4e to the t, e to the 4t, e to the 4t. I'm just copying columns. And then phi 0 inverse, so we have this factor of 1/3. 1 minus 1 minus 4, 7. And I'm just going to pull the 1/3 out in front, leave it there. And then we'll have 7 e to the t minus 4 e to the 4t minus 7 e to the t plus 7 e to the 4t. We'll get 4 e to the 4t, 4 e to the t minus 4 e to the 4t. And finally, we'll get minus 4 e to the t and plus 7 e to the 4t. And there we go. All right, so distinct real. Our plan is find eigenvectors. Eigenvalues, eigenvectors give solutions. That gives us our columns for a fundamental matrix. If we have a fundamental matrix, we can find the fundamental matrix. E to the AT is really special using our formula, 5t, phi 0 inverse. And we put it all together. Life is good. Life is wonderful. We got our answer. Nice. Nice. Number 4. Find e to the AT for the matrix 1, 4, minus 2, 5. All right. Well, when we're looking for e to the AT, we have one of 3 possibilities. And we have to know which thing are we in. Repeated eigenvalues, distinct real eigenvalues, complex eigenvalues. And all of that is determined by, hey, what are your eigenvalues? So, here we go. Let's compute them. A minus lambda I. So we're going to take the determinant, 1 minus lambda, 4 minus 2, 5 minus lambda, which, okay, that becomes 1 minus lambda times 5 minus lambda, subtract negative 2 times 4. And, well, that's lambda squared. And then we're going to have a minus lambda and a minus 5 lambda. That's minus 6 lambda. And then there's a 5, but there's also a 5. And we have here a plus 8. 5 plus 8, 13. Okay. And, I don't see a good way to factor that. And the more I stare at this, the less sure I get how to factor it. Because what do we see? Well, how can we multiply and get 13? Not very many ways, 1 and 13. But there's no way to combine 1 and 13 and end up with 6. So it's not going to factor nicely. So what can we do? Well, what we can do now is say, well, let's either do a quadratic formula or complete the square. Let's do complete the square. I like to do a little bit of complete the square work. So if it doesn't factor nicely, complete the square really follows from quadratic formula, or vice versa, I should say. They're tied together. So you have lambda squared minus 6 lambda, and you say, well, what would I want to add here if I wanted something which was a square? I mean, we call it complete the square, so you want a square. You take the negative 6, divide by 2, go to negative 3, and square it. And so if I stop there, this part is a square. Lambda minus 3 squared by design. But wait a second, we don't have plus 9, we have plus 13, which means that we have 4 more left over. Or lambda minus 3 squared plus 4 equals 0. And now we say, oh, I can see what's going to happen. This, normally when you square something, you end up with something positive or greater than or equal to 0. And this is plus 4. Hard to get to 0. Unless what we square gets us a negative thing. And that sounds a little bit complex. All right. Finishing up, we have lambda minus 3 squared is negative 4, which means that lambda minus 3 had to be plus or minus 2i. The I because of the negative when we take the square root. Or lambda equals 3 plus minus 2i. That means we're in complex roots. And the next thing I want to do before I grab my formula sheet, because we're definitely grabbing our formula sheet, there's ways to find e to the at without the formula sheet. We are not going to do that because we want to be nice to ourselves. We like ourselves. And so we want to make sure that we give ourselves the best chances of minimizing error. Okay, so what am I going to do before I grab the formula sheet is to note that this looks like an alpha plus minus beta I, where, okay, alpha to be explicit is 3, and beta to be explicit is 2. All right. Now, formula sheet time. And the formula for e to the at is the big, long one. So I'm going to write that again for reference. And it says e to the at is e to the alpha t cosine beta t times the identity plus 1 over beta e to the alpha t sine beta t times a minus alpha I. All right, so we grab the formula from the formula sheet. And we say, well, what do we know? Well, we know alpha and beta. We said it right here. So we just start putting in what we know. So we have e to the 3t cosine 2t, right? Alpha is 3, beta is 2. I means matrix 1, 0, 0, 1. Plus 1 over beta, well, that would be 1 over 2. Beta's a half. Then we have e to the 3t sine of 2t. All right. And then we have our a minus alpha I. Now, it's like a minus lambda I. It's just we choose the value for alpha. So what are we going to subtract? Well, so we're going to take our matrix and subtract 3. So it's like we're subtracting 3. So 1 minus 3 is minus 2. And then we have 4 and minus 2. And 5 minus 3 is a plus 2. And that's the answer. You're like, wait a second. You have all this space. You're right. So let's do one more thing. Let's go ahead and put it into one matrix. But this is correct. This is correct. So if we put it into one matrix, it'd be a big matrix. So the first entry in the upper left, well, we would get e to the 3t cosine 2t. And then this upper left entry, don't forget about the half. The half times minus 2 makes a minus 1, e to the 3t sine of 2t. Okay, how about this upper right? Well, here, 0. Okay, hard to recover from 0. 4 times a half makes a 2, e to the 3t sine 2t. And that's the upper right. Okay, how about lower left? Well, times 0, hard to recover. Half times minus 2 makes a minus. And then we have an e 3t sine 2t. And then lower right entry, okay, we have e 3t cosine 2t times 1. A half times 2 makes a 1. So plus a 1, e to the 3t sine of 2t. And that's the answer in one big matrix. Wow. Once you have the tool, that makes life more straightforward. We can put in a lot less work. Because what do we have? We have e to the at, which gives us so much. You say, okay, what does it give us? Well, what if I asked you for general form? Now you might say, oh, I guess we've got to go back and find No, we're not going to find eigenvectors. Here's x1, here's x2, superposition. Really? That's it? Yes, that's it. What if I have initial values? Oh, it's e to the at times it by initial value vector. That's it? Yes, that's it. You know, that's the power. We get to jump to the end. Instead of having to trudge along. It's like, no, go right to the end. And then we can slide back if we need to. It's nice to have good tools. Beautiful, beautiful. Number 5. Find e to the at for a is 2 minus 9, 1, 8. All right, we have a matrix A. We're asked to find e to the at. We need to know which one of our 3 settings we're in. So let's start by finding our eigenvalues. Okay, so our eigenvalues of A. And always our first step, because that's going to tell us the road that we're going to travel. Take the determinant of A minus lambda I. So we have our determinant, 2 minus lambda, minus 9, 1, 8 minus lambda. And all right, that's 2 minus lambda times 8 minus lambda. Subtract 1 times minus 9. And we expand. And that would be a lambda squared. We have a minus 2 lambda, minus 8 lambda, minus 10 lambda, 16 plus 9. Right, minus, minus. And 16 plus 9 makes 25. And we're like, ooh, I think I see what this is. This is lambda minus 5 squared. And we set that equal to 0. And what does that tell us? It tells us that we have a double root, or a repeated root. 5, 5, repeated root. Or I guess I should say repeated eigenvalue. All right. Cool. Now, we know what setting we're in. So, all right, grab our formula sheet. Okay, boom, grabbed it. And we said, well, which one of these formulas is repeated? It's this one. And so I'm going to write that formula down. It says that e to the at is e to the lambda t times the identity plus t, a minus lambda I. All right. Well, what do we have? Well, we have lambda. Lambda is 5. So we say, okay, so this is e to the 5t. All right. And then what? Times the identity. Well, that's 1, 0, 0, 1 plus t times, and then we're going to put a minus lambda I. So lambda is 5. So a minus lambda I, 2 minus 5, minus 3, minus 9, 1, and, sorry, lambda is 5, 3. Good. All right, well, that's correct. We'll just clean up a little bit. E to the 5t, and on the inside we'll get 1 minus 3t, and then we'll get 0 minus 9t, and here we'll get 0 plus t, and we'll get 1 and plus 3t. And depending upon how you want it, some people like this first thing we wrote down. Some people like the second thing. Some people like the third, which we're about to write down. Multiply the e to the 5tn. And whichever way you like to write it, as long as the instructions allow it, I think all three are great answers. But I'm going to throw a box around the last one we put down. And there we go. You're like, wait a second. That seemed way too easy. That's the point. We work hard to get these formulas so that we can make problems more straightforward. That's the goal, right? We want life to be simpler. We got to work to get there. But once we get there, let's use what we learned and make life better for ourselves. Number 6. We're asked, find xp. So that means a particular solution for x prime is 2, 3, 4, 1, x, and this plus t plus 5 minus 3t minus 3. So here, the thing is, what's going on? We have here what we might call f of t. And in particular, that says, wait a second, this part is a non-homogeneous differential equation because we have something on the end. All right, so how do we handle it? Well, we have to find a particular solution. And we say, all right, well, what do we do? Well, we start by saying, let's take a little peek at xc. Now, just a little peek. You don't have to take a big peek, just a little peek. And what do we need to do? Well, we need to get a rough idea of what the solutions look like. And we don't even need to get the full solutions. In fact, all we really need to understand is what do the eigenvalues look like? Okay, so let's cut to the chase. All right, let's go ahead and do this really quickly. So I'm going to find the eigenvalues of A, and just so there's no ambiguity, this is what I mean by A. Eigenvalues of A. And, well, okay, so we take our determinant A minus lambda I. That's 2 minus lambda, 3, 4, 1 minus lambda. Well, that's 2 minus lambda times 1 minus lambda. Subtract 4 times 3, which is lambda squared. Minus 2 lambda minus lambda makes minus 3 lambda. A plus 2 minus 12 is minus 10. Which says, actually this one factors, which is nice. Lambda minus 5, lambda plus 2. And since we're saying equal to 0, we say, we have the following. We have the eigenvalues are 5 and negative 2. Now, since we're only after xp, we don't have to keep pushing. The only thing that we really need to extract from this is that we get a solution that looks like e to the 5t times something, and a solution that looks like e to the minus 2t times something. And I don't know what those somethings are. Those are the eigenvectors, and I'll explain why that's all we need to know in a few moments. Okay, so now let's turn our attention to xp. For xp, when we look at this particular f of t, it's nice in the sense that this is something that could come out of a constant coefficient, linear, homogeneous differential equation, right? Taking our mindset back to what we were doing in the previous part of the course. And so what we say is like, okay, well, we're going to make a list. And our list is a very simple list. And we say, what functions are involved in this f of t? Well, f of t has two types of functions, namely constants and t's. And now we check three things. I'll do an easy one. Do sines and cosines come in pairs? Yes, because there are no sines and cosines, so they come in pairs. When I have something with the power of t in front, do I have all the lower powers of t? Yes. Here's t. The lower power of t is t to 0, which is 1. Do I have overlap with xc? Now, for xc, I don't need to look at the eigenvectors. I need to look at the functions. And those are coming from the eigenvalues. So that's what I'm looking at. And I say, well, this would be e to the 5t, e to the minus 2t. None of those are on the list, so no overlap. So we don't have to do any correction. All right, so that's why I didn't need the eigenvector. I only needed eigenvalue to check to see if there were going to be overlaps with the functions involved. All right. So what does this tell us? Well, what this tells us is that xp has a very particular form. xp looks like the first function times some unknown vector, I'll use ab, plus the second function times some unknown vector, cd. Or, if you like, we can just sort of cram it together, a plus ct, b plus dt. And now we have to figure out a, c, b, d. So how do we figure it out? We run it through the equation. It's like we're trying to verify. And so we say, okay, well, let's look at the left-hand side, xp prime. So take the derivative. What do you get? Well, you get cd. Okay, so this is xp prime. That's supposed to be equal to 2, 3, 4, 1 times a plus ct, b plus dt, plus t plus 5 minus 3t minus 3. Here's our xp. Well, let's clean up this right-hand side. And that's going to take us a minute or two to go through that. We'll start by multiplying this out. So this is 2 times a plus ct plus 3 times b plus dt plus t plus 5. All right, that's just first entry. And we're going to get 4 times a plus ct, right? 4 times a plus ct plus 1 times b plus dt plus minus 3t minus 3. Okay. Or we're going to enter into our sort of hunter-gatherer phase and say, let's find all the things attached to the t and all the things attached to the constants. So for t's, you'll notice we have a t, a t, a t, 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 t. So when we gather our t's, we get t times 2c plus 3d plus 1. Downstairs we have t times 4c plus d minus 3. Now we'll gather our constants. So we have constant, 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 constant. So our constant terms look like plus 2a plus 3b plus 5 plus 4a plus b minus 3. And remember, all of this has to equal CD. And now we say, well, wait a second. These two vectors are equal, which means, of course, every entry is equal, which means what? it means that the corresponding coefficients must be equal. So, for instance, we get that 2a plus 3b plus 5, which is our constant, has to match our constant, has to be c. This 4a plus b minus 3, which is our constant, has to match our constant, which is d. But what about these terms here? There's no t on this side. So what must be true? They must be 0. So we now have 4 equations and 4 unknowns. Oh, but it's actually not as bad as it sounds. Because what's going to happen is we're going to go through in a couple rounds. Okay, so what we're going to do is we're going to start off with our highest power of t. And so we'll start here in our first round. And if you look there, you'll notice there's only 2 unknowns, c and d. So that's why we want to focus our energy there first. And we say, okay, so what does that tell us? Well, we get that 2c plus 3d. I'm going to move that 1 over. Has to be minus 1. And 4c plus d has to be positive 3. And we start saying, well, okay, we want to do some cancellation. I would multiply this first one by minus 2 and then add, because then we get the c's canceling. Okay, so minus 4c plus 4c, 0. Minus 6d plus d is minus 5d. 2 plus 3 is 5. So that tells us d is minus 1. All right, we got one of our unknowns. Once we know d, plug it in. So here, for instance, we can say 4c plus d minus 1 is 3. Or, let's see, I can move this up a little bit. Yeah, there we go. 4c is 4, or c is 1. Okay, so we have d is minus 1, c is 1. Okay, so I'm going to come up here and just make some notes. C is 1, and d is minus 1. Okay, now that we had those solved, now we come in to these rounds. Okay, so what do we have? Well, we have the following. 2a plus 3b is equal to, remember c we've already solved for, c is 1. So it's 1 subtract 5, negative 4. Okay, where did that negative 4 come from? C is 1, 1 subtract 5. 4a plus b is equal to what? Well, d is minus 1, but then we're going to add 3. Minus 1 plus 3, 2. All right, so 2 equations, 2 unknowns. But notice it was important for us to solve for c and d first, which is why we started with our t's. Okay, well, we're going to run the same process. If we multiply the first equation by minus 2, and then we add, well, the a's cancel. We'll get minus 6b plus b is minus 5b. 8 plus 2 is 10. And we say, oh, that says b is negative 2. Now you know what b is. Plug it in. 4a minus 2 is 2. And we can add 2 to both sides. 4a equals 4, or a equals 1. Okay, so b equals minus 2. So we have a minus 2. And then a equals 1. So we have a 1. And now we're done because we have our values. So we're ready to write down our final answer. It's great when we get to the end, right? So our xp, we said our xp has this form. We ran it through the differential equation, and then by comparing coefficients, we said, oh, that tells us what a, b, c, and d have to be. So we get that our answer is a plus ct becomes 1 plus t, and then b plus dt becomes minus 2 minus t. And that is our particular solution. So this satisfies the original differential equation. Nice! Woohoo! Number 7. Verify that there's this function e to the 2t times 3t squared plus t minus 9t squared plus 3t is a solution to x prime is 5, 1, minus 9, minus 1x plus e to the 2t, 1, 3. Also, give the general form for solutions. All right. So, what do we do? So what it's asking us to do is to say, hey, we claim that this part right here is a solution. In other words, that is an XP. But we have to verify it. And we say, okay, so let's start by verifying. So what do? Well, we have to plug it into both sides. So we're verifying our XP. Okay, so the left-hand side, that's XP prime. And, okay, so, well, it's a product rule. So get rid of the first, 2e to the 2t, times the second, 3t squared plus t, minus 9t squared plus 3t, plus the first, e to the 2t, times the derivative of the second. All right, take the derivative of each entry. 6t plus 1 minus 18t plus 3. So, all right, great. And for comparison, let's put this together. Everything's going to have an e to the 2t, so I'm just going to pull that out, leave it out in front. Here we have a 2 times a 3t squared. That makes a 6t squared. Notice there's no t squared here. 2 times t makes 2t plus 6t. That makes an 8t. And there's no constant, but here there's a constant, plus 1. All right, bottom. 2 times minus 9t squared minus 18t squared. Then we're going to have 2 times 3t, which is 6t, minus 18t. 6 minus 18 will get us to minus 12t. And then the only constant is here, plus 3. All right, so there's the left-hand side. All right, now we have to do the right-hand side. And what do we get there? Right-hand side. So we're going to look at 5, 1, minus 9, minus 1, times xp plus e to the 2t, 1, 3. Okay, so that's our 5, 1, minus 9, minus 1, times e to the 2t, times 3t squared plus t, minus 9t squared plus 3t, plus e to the 2t, 1, 3. Well, okay, that is, as we're very patient here, e to the 2t is common to both, so I'm going to pull that out. So we're going to get 5 times this entry, so 5 times 3t squared plus t, plus 1 times the minus 9t squared plus 3t, and then add one more. And then we're going to get minus 9 times 3t squared plus t, and then we're going to have a minus 1 times minus 9t squared plus 3t, and don't forget a plus 3. Well, that makes e to the 2t times, and okay, we get 15t squared minus 9t squared, that's 6t squared, 5t plus 3t, that's 8t, and plus 1, minus 27t squared plus 9t squared minus 18t squared, minus 9t minus 3t minus 12t, and plus 3. And now we say, okay, well, do they match? If they don't, mistakes were made. Hopefully not by the person who wrote the problem, but yes, these two indeed match, and so that's the verify. Okay, whew. Okay, we got the verify done. Now, we have xp. What do we need? xc. And that looks like it's going to take us a long time. Or will it? I think there's a shortcut here. Let's look at this. Let's put on our thinking caps for a moment. Okay, so we put on our thinking caps. And we're saying, this is a nice kind of problem, right? The e to the 2t is something that could come out of a nice kind of differential equation. And so normally, if we were making a list, we'd say, well, our list would be fairly short. The only function involved is e to the 2t. But when we got to the end, what did we end up with? Well, we ended up with having t squared e to the 2t and t e to the 2t being the pieces of our function. So what happened? The only thing that could have happened is to say, oh, there must have been some overlap going on. And we're like, oh, in fact, this says, oh, there was overlap with our xc. How much overlap? Well, enough that we had to go up 2 steps. We had to add in 2 additional layers. So what does that tell us? So the overlap with xc tells us, or I'll be fancy and use the word, it indicates that the eigenvalues must be 2 and 2, right? Because the only way we could overlap is if we had 2 as an eigenvalue, but because we had an overlap of 2, it had to occur twice. So we say, oh, we are in repeated eigenvalues. And so we say, aha, so we know that the eigenvalues of our matrix 5, 1, minus 9, minus 1 are 2, 2. How does that help us? It helps us a lot because it says, oh, wouldn't you know it? We can skip finding eigenvectors and other things and jump ahead and get e to the at. So I'm going to grab e to the at. So we have a nice formula for e to the at. And so e to the at is e to the lambda t times the identity plus t times a minus lambda I. And I'm just going to quickly double check because I'm paranoid that I wrote that down correctly. E to the lambda t, identity plus t, a minus lambda I. Okay, yeah, that's good. So, in our case, this would be e to the 2t, identity is 1, 0, 0, 1, plus t, and then we take our a minus lambda I. So we're subtracting 2 off the diagonal. So 5 minus 2 is 3, 1 minus 9 minus 1 minus 2 is minus 3. Or that's e to the 2t, and we'll just put these together. We get 1 plus 3t, t, minus 9t, 1 minus 3t. Or this is, if we just multiply the e to the 2t in, we get 1 plus 3t e to the 2t minus 9t e to the 2t, t e to the 2t, and 1 minus 3t e to the 2t. And here's our great aha. We've alluded to it before, but now we can be very explicit and say, look, it's happening. It's really, really happening. This is a fundamental matrix. There are many. This is a good one because we found it pretty quickly. What's true about a fundamental matrix? A fundamental matrix is formed by making the columns solutions. So, solution 1, solution 2. And XP is now, sorry, not XP, XC is some constant solution 1 plus some constant solution 2. And so to be more explicit, we can say, okay, here's x1, just pull out the vector, and I'll go ahead and pull e to the 2t back out because that's common. And we have 1 plus 3t minus 9t. And then solution 2, C2, again, e to the 2t I can pull out. And we're left with t and 1 minus 3t. All right. Well, with all of that work done, now we're ready to put it all together. Okay, so here we go. Here we go. Our final answer, because we want general form, our final answer is to say x is xc plus xp. Here is our xc. We were able to grab it pretty quickly. And even if you didn't see the bumping, it wouldn't take you very long to just go through and find the eigenvectors. So seeing that the eigenvectors were repeated doesn't save you that much time, but it's a fun little observation. And oftentimes, you start to pick up like, oh, here's an idea. Let me use it. Then don't forget you have our last piece, your xp, e to the 2t times 3t squared plus t minus 9t squared plus 3t. And there we go. That's our final answer. Whew. Yes. Good. We made it. Whew. Some of these problems I get a little bit nervous because it's like, do I have enough space on the page? But it's not that any computation is particularly hard. It's just that you have to do a lot of computations because there's a lot of things happening simultaneously. So don't be overwhelmed. If you just walk in casually like, whoa, this is scary looking. You don't have to be scared. It's not meant to be frightening. You just practice and say, look, there's a process, step by step, carefully carry out, and you'll be great. You'll be wonderful. All right, let's keep going. Number 8. Find the general form for x prime is minus 2, 3, 2 minus 1x plus 2e to the 2t, 8e to the 2t. All right, well, good. So we have our x prime equals ax. So here's our a. And then we have an f of t. So this is a non-homogeneous. All right, okay, well, no problem. We can handle that. We are not intimidated by non-homogeneous problems. So what do we do? What do we do? Well, the first thing is you have to look at the homogeneous piece of it and say, okay, well, let's focus on the x prime equals ax. And for that, we say, well, start with the eigenvalues, because that will tell you how to proceed. So what are the eigenvalues of a? All right, well, we're taking the determinant a minus lambda I, and so that's the determinant. Minus 2 minus lambda, 3, 2, minus 1 minus lambda, and so that's minus 2 minus lambda times minus 1 minus lambda. subtract 2 times 3. And, all right, well, that's lambda squared. And then what? Well, we have a plus 2 lambda plus the lambda, so that's plus 3 lambda plus 2, and minus 6, minus 4. All right, so what do we need? Two numbers who would multiply together to get minus 4, add together to give 3. Can we think of that? I think there's some reasonable candidates. So let's try this. 3 is positive, so the thing that jumps to mind is 4 and 1. So I think if we make the plus 4 and minus 1 should work. Let's try it. Lambda squared, good. Minus lambda, plus 4 lambda, 3 lambda, good. Minus 4, good. All right. And we set it equal to 0, and we say, well, that gives us two distinct eigenvalues. And like, all right, so we have lambda is -4, lambda is 1. Now, when we're faced with two distinct real eigenvalues, we've got to go and find our eigenvectors. All right, so that's going to be our next step. So we say, well, eigenvector time. Let's try this out. When we put in lambda equals -4, so we're going to subtract a minus 4 or add 4. So minus 2 plus 4 makes 2. Then we have 3, 2. Minus 1 plus 4 makes 3. We're timesing it by something. We want to get 0, 0. Okay, well, not a lot of choices. Pick a row, 2, 3. Seems like a really good row. And then we'll write things in reverse order. 3, 2. And then we'll flip a sign. So 3 minus 2. All right. So that gives us that we have lambda equals -4 and eigenvector 3 minus 2. Which really says what? Well, it tells us we have a solution to the homogeneous part that looks like e to the minus 4t times 3 minus 2. Okay, we still have another eigenvalue to do. Lambda equals 1. Okay, so subtract 1. Minus 2 minus 1, minus 3. 3, 2. Minus 1 subtract 1, minus 2. All right. Times something needs to give us 0, 0. Okay, well, do you see anything that works? You can pick a row, but if you can see something even nicer, I see something pretty nice. 1, 1. Right? Minus 3 plus 3 is 0. 2 minus 2 is 0. So that definitely works. You can do the same row thing if you want, but again, if you see something, try it out. And if it works, great. If it doesn't, try something else. Right? That's how you solve problems. Try something. If it doesn't work, try something else. But don't give up. There's always something. All right, so we have e to the eigenvalue t, e to the t, 1, 1. Okay, so now we've really nailed down our homogeneous part. And in particular, we'll not write it fully out, but the punchline here is our xc is some constant c1 x1 plus c2 x2. So we turn now to our particular solution. And we see something pretty nice, e to the 2t. That's something that could come out of a differential equation. And so we say, okay, since it's something nice, let's use that to our advantage, and we'll do our method of undetermined coefficients. And so that's where we begin. So we say, okay, let's make a list. And we look at our f of t and say, what are all the functions that are showing up in our f of t? That's just one. One function showing up, which is e to the 2t. Now, we check. Sines and cosines come in pairs. Good. If I have any powers of t in front, I don't, so that's good. Do I have overlap? Well, e to the 2t versus e to the minus 4t, e to the t, no. So that makes the list really easy to work with. We like this list. This is a good list. So we say, okay, keep with that list. Now, what does that tell us? Well, with our list in place, it tells us the following. Lo and behold, and I should have written down, just for reference, we're doing undetermined coefficients. So what this tells us is that xp looks like e to the 2t times some vector. Well, we don't know. That's the undetermined part. So we say, okay, we'll throw in some unknowns, a, b. How do we find a and b? We're going to run it through our differential equation. Okay, so we get that take the derivative of e to the 2t will be 2e to the 2t, or if you like, e to the 2t, 2a, 2b. And to be clear what this is supposed to represent, so there's no, wait, what is this again? This is xp prime. That's supposed to be equal to minus 2, 3, 2, minus 1 times, well, a e to the 2t, b e to the 2t, plus 2e to the 2t, 8e to the 2t. Okay, so here is our xp. And now we'll just clean this up. We get the following. We'll get minus 2a. Everything has e to the 2t. I'm going to just pull that in front. Minus 2a plus 3b plus 2. 2a minus b plus 8. And these have to match. So, what does that say? It says that this piece must match this piece. And simultaneously, that this part must match this part. So we have two equations. Two equations, two unknowns. It's a very good mix. So just setting the parts equal, the e to the 2t's are the same in both parts, so they don't play a role. It's really the coefficients of the functions. That's what drives the method of undetermined coefficients. So we have 2a is minus 2a plus 3b plus 2. Or, if we move things around, this becomes 4a, right? Because you add 2a minus 3b equals 2. Okay, so we just move things across. We also have 2b is 2a minus b plus 8. Well, that becomes minus 2a plus 3b equals 8. All right, two equations, two unknowns. Bread and butter. We got this. Like we were built for this. We've been doing this for so long. We can do this in our sleep. For example, if we add them up, the b's will cancel. Almost as if it was meant to happen. Because, well, we've been living a good, clean, calculus life. So yeah, good things should happen. 2a should equal 10. That tells us a should be 5. Well, once we know a equals 5, plug it in to either equation, doesn't really matter. 20 minus 3b should be equal to 2. Or 3b should be equal to 18, or b equals 6. So what does that tell us? It tells us what A and B are. Now, why do we care about A and B? Because that shows up in our XP. So we say, oh, updating, this means we have e to the 2t times A equals 5, and B equals 6. 5, 6. So, we're at the end. One more thing for us to do, which is we need to write down our answer. Okay, all right. So our final thing is we combine our complementary with our particular. So our complementary comes from what we did over here. So we get some constant, e to the minus 4t, 3 minus 2, plus some constant, e to the t, 1, 1, plus our particular, plus e to the 2t, 5, 6. And that, whoops, excuse me, and that is our answer. Wow, nice, nice, we did it. Good job, us. High fives. All right, well, let's keep moving on. Number 9, we're asked, find XP, our particular solution, for x prime is 5 minus 3, 3 minus 1x, plus 9 root t e to the 2t, minus 6 root t e to the 2t. And it says, hint, the eigenvalues are 2, 2. Now, we're non-homogeneous, and when it talks about eigenvalues, that's referring to these eigenvalues. So this is our matrix A. And here, this is our f of t. So non-homogeneous, but not only are we non-homogeneous, there's some bad news. Look at the kind of function we have showing up in our non-homogeneous portion. It is not nice, right? That square root of t, not a pleasant thing to work with. Darn it. Well, excuse my salty language. I shouldn't say darn it. It really, we should say what? It means like, well, interesting things are ahead. So we cannot use method of undetermined coefficients. That's out. So what can we use? Well, what we can use is we can use our variation of parameters. Okay, so what does that say? Variation of parameters. It says that if you're looking for xp, that is e to the at integral e to the minus at times f of t dt. So that's what we're going to run through. We're going to do that computation, and then we'll have our particular solution. And you're like, okay, how bad could that be? Hopefully not bad. Fingers crossed. But there is a bit of work. We have a lot of layers to get through. Variation of parameters is definitely qualifying for what I would call an onion-type problem. Lots of layers involved. And possibly some tears will be shed by the time we reach the end. But we're not going to panic, because that won't help us. So where do we begin? Well, when you're doing variation of parameters, you need to either find a fundamental matrix or find like the really nice fundamental matrix, e to the at. We're going to lean into their hint and say, well, they gave us the eigenvalues, so let's use that to our advantage. Since we know what the eigenvalues are, they're repeated, and we say, well, wouldn't you know it? For repeated eigenvalues, we have a nice shortcut for e to the at. So I'll write that down. We have that e to the at is equal to e to the lambda t times the identity plus t a minus lambda I. Now for us, our eigenvalues are 2 and 2. So that says lambda is 2. So e to the 2t, 1, 0, 0, 1, plus t. And now subtract 2 off the diagonal. And that would give us 3 minus 3 and 3 minus 3. And, okay. And so e to the 2t, we have 1 plus 3t minus 3t. And what else do we have? We have 3t and 1 minus 3t. Okay, so there's e to the at. Now we're going to start working through this in layers, one layer after another. Let's start with our first layer. And what I'm going to call our first layer is this computation here, e to the minus at f of t. Layer number 1. E to the minus at f of t. Now, how do you find e to the minus at? The answer is everywhere where you see a t, put a minus t. So we get e to the minus 2t, 1 minus 3t, 3t minus 3t, 1 plus 3t. Okay, so this is everywhere where we had t before, put a minus t. Now, what about f of t? Well, let's go ahead and pull out anything common. What's common? Well, I'm going to pull out a t to the 1/2, square root of t, and an e to the 2t. And then we'll have a 9 and a minus 6. Now, you might notice something that will help simplify things really quickly. These cancel. Nice. So, what do we get? Well, we get a t to the 1/2. And now we'll just carry this out. So we have 9 minus 27t minus 18t. Then we have minus 27t. And then we have minus 6 minus 18t. All right, so, and, well, I'm going to move the t to the 1/2 back in. But as we do that, we'll clean it up. So we have 9 t to the 1/2 minus 27 minus 18 makes minus 45. So minus 45 t to the 3/2. Here we have a minus 6 t to the 1/2. Minus 27 minus 18 is again minus 45 t to the 3/2. All right, so that's layer 1. We've gone into our onion. We are definitely inside the onion. Now, layer 2 says what? Well, do the integral. So that's our second layer. Okay, so here's layer 2. We're going to do the integral e to the minus at f of t dt. Well, okay, so that's the integral of our 9t to the 1/2 minus 45 t to the 3/2 minus 6t to the 1/2 minus 45 t to the 3/2 dt. And how do we integrate? Term by term. Since we're after xp, we don't need to add constants. So, we're going to have 9, and integral t to the 1/2, well, that's t to the 3/2, but times by the reciprocal, 2/3, minus 45, t to the 5/2 times by the reciprocal, 2/5. Downstairs, minus 6, again, t to the 3/2, but multiplied by the reciprocal, and minus 45 again, t to the 5/2 times the reciprocal. Well, if we clean this up, which, we should. We have 18 thirds, which gives us 6 t to the 3 halves. 90 divided by 5, or if you like 45 divided by 5 is 9 times 2. So 18 t to the 5 halves minus 12 over 3, and that makes minus 4 t to the 3 halves. And then we have, again, minus 18 t to the 5 halves. Okay. Good. Progress. We're in. Now we're reaching the end. And that's not just because we're running out of space on the page. We really are close to the end, right? So the last thing, the last layer, our third round, is we're going to now multiply what we just did by e to the at. So we want e to the at times the integral e to the minus at f of t dt. Well, we have e to the at. So that's e to the 2t times 1 plus 3t, 3t minus 3t, 1 minus 3t, times this beautiful expression, 6t to the 3 halves minus 18t to the 5 halves minus 4t to the 3 halves minus 18t to the 5 halves. All right, now this is a matrix, this is a vector. Sometimes this starts looking like a matrix. Make sure you keep track of things. Okay, matrix vector. So we have our e to the 2t times, well, we're going to take 1 plus 3t times our 6t to the 3 halves minus 18t to the 5 halves minus 3t minus 4t to the 3 halves minus 18t to the 5 halves. Okay, 3t times 6t to the 3 halves minus 18t to the 5 halves. And then there's going to be a 1 minus 3t times minus 4t to the 3 halves minus 18t to the 5 halves. All right, now we're going to clean this up. And I think I'm going to clean it up over here. So I'm going to do this in 2 rounds. So just so I don't get lost on what is what, I'm going to color code my simplifying. So here goes the green. So let's do our green. We're going to distribute. So we're going to get FOIL here. So we have 6t to the 3 halves and minus 18t to the 5 halves. Then we're going to get a 3t times 6t to the 3 halves. And what will that be? Well, actually, that's 18t to the 5 halves. So there's a plus 18t to the 5 halves. Okay, and then there's a 3 times 8 makes 54. So minus 54t to the 7 halves. Right, that's t times t to the 5 halves. Over here, we'll have a minus 3t times minus 4t to the 3 halves. That's a plus 12t to the 5 halves. And then we'll have minus 3t times minus 18t to the 5 halves. Well, that's going to be a plus 54t to the 7 halves. So plus 54t to the 7 halves. And now we're like, oh, pew, 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 pew. Which tells us that once we expand and then group, we get, for the first entry, right? This is only the first entry. 6t to the 3 halves plus 12t to the 5 halves. All right, that's the first entry. And you might say, wait, what? That seems like a lot of collapse. It frequently happens just because of the nature of how we go about solving it. Cancellation is not unusual. In some sense, it's expected. All right, now, halfway done, right? There's still another half to go. So we're going to do our other half. And let's switch colors so we don't confuse ourselves more than we already have, right? No, we're doing great. We're doing great. No worries. Okay, so we start distributing. We'll have 3t times 6t to the 3 halves. That makes 18 t to the 5 halves. And then we'll have 3t times minus 18t to the 5 halves. That's a minus 54. And then it'll be t to the 7 halves. Then we'll get a minus 4 t to the 3 halves. A minus 18 t to the 5 halves. Right? 1 times minus 18. And then we'll have a minus 3t times a minus 4t to the 3 halves. Minus 3 times minus 4 makes a plus 12. And then we'll get t to the 5 halves. And then finally, minus 3t times minus 18, minus 3t minus 18t to the 5 halves makes a plus 54 t to the 7 halves. And again, cancellation. So what are we left with? Well, we're left with the following. Minus 4 t to the 3 halves plus 12 t to the 5 halves. And then we're done. Yes, yes. Now, one of the downsides about variation of parameters, maybe I shouldn't say one of the downsides, but one thing that does happen is there's a lot of computation involved. And certainly a lot of things that can make it more challenging. You can get integrations that get really unpleasant very quickly, as a lot of integrations do. And then you get long expressions that ends up collapsing to a degree. So I don't want you to look at this and say like, this is terrible, I would never use this. Because sometimes you have to go through and do something which is a little bit computational. Take your time. Pace yourself. You can do this. You can do this. Just work through your layers. One layer of onion at a time. You'll be great. Don't worry. You got this. Our last problem. Number 10. Woo! Find a particular solution, xp, for x prime is 0, 2, minus 2, 0, x plus 0 secant squared t. And they said, look, we're just going to let you jump ahead. We'll tell you what e to the at is. Phew, that's going to make our life a little bit simpler. All right, so notice here, this 0 secant squared t, this part right here, this is our f of t. And looking at it, you see secant squared, and like, secant, that's not nice. It doesn't come out of a nice differential equation, meaning we've got to run through variation of parameters. Okay, so not nice. I'll put in quotation marks. I mean, I don't want to get people thinking like secant squared t is a mean function. It's just it's not one that comes out of a nice differential equation. All right, so variation of parameters. And the good news is they did some work for us, so that will save us a step. And all right, so let's remind ourselves. We get that xp is e to the at integral e to the minus at f of t dt. All right, so that's what we need to compute. We have layers. There are definite layers in this problem. So we start with our first layer, computing e to the minus at f of t. All right, so layer 1, e to the minus at f of t. Now, they gave us e to the at. How do you find e to the minus at? The answer is, everywhere you see a t, put a minus. Now, we want to clean it up. Cosine minus 2t. What can we say about that? Well, cosine is even, so it's cosine 2t. Sine of minus 2t. Sine is odd, so it's minus sine of 2t. Here, minus sine of minus 2t. We have an odd function, so that comes out, and minus minus makes a plus. Cosine minus 2t, even, cosine 2t. And then we have our f of t, 0 secant squared t. Well, if we multiply this out, we're going to get the following. We'll get 0, and then minus sine of 2t, secant squared t, 0, cosine of 2t, secant squared t. Well, looking ahead, there's an integral coming. And so since we know there's an integral coming, we're going to say, let's be nice to ourselves, and let's rewrite this in a very friendly-ish way. And one thing you might notice is to say, these insides aren't matching. You see some 2t's in some places, and then you see t's in other places. That's just apples and other types of apples, right? They're not compatible. So we want to replace them. And so one thing we can do is say, well, sine of 2t, we can replace that by minus 2 sine t cosine t, and then we have our secant squared t. Cosine 2t is interesting because there's a lot of different ways to do cosine 2t. Cosine is cosine squared minus sine squared, and then you can do a couple of different variations of that. And one variation that's particularly helpful for us is it's 2 cosine squared minus 1, and times by secant squared t. Now, if we clean this up just a little bit more, secant is 1 over cosine. So a cosine times a secant cancels. And so what do you have? Well, you have a sine and 1 secant left. And a sine times a secant is a tangent, meaning the first entry becomes minus 2 tangent t. Cosine squared times secant squared, 1. So that's a 2. And then we have a minus secant squared. And now all of these are going to make our next step more palatable. So what's our next step? Our next step is we're going to integrate. Okay, so that's step 2. So here we go. The integral of e to the minus at f of t dt. Well, that's the integral of what we just found. And because we invested, I said, well, let's make it nice. This will be a quick step for us. Integral of tangent, log secant, integral of 2, 2t, integral of secant squared, tangent. And we don't need to worry about constants because we're after xp. That brings us to our last step, working through our layers, our final layer of onion, 3. So that last step says the following. Okay. So for 3, we're going to take e to the at times what we just found. Well, that is our function cosine 2t, sine of 2t, minus sine of 2t, cosine of 2t, right? That's our e to the at. They gave it to us. Times what we just found, minus 2 log secant of t. And then we have 2t minus tangent of t. And we work it out, right? So we do our multiplication. We'll have a minus 2 cosine 2t log secant t, okay, plus sine of 2t times 2t minus tangent of t. Okay, so we boom, boom. And there's nothing looking like we're going to get cancellation, so I'm not going to bother simplifying. I'm not going to bother expanding. Here, we'll get a plus. We'll get a 2 sine of 2t, and we'll have a log secant of t, plus a cosine 2t times 2t minus tangent t. And scene, right? We're done. We're done. That is XP. So we box it. And we're like, yep, definitely would not have guessed that. Whew, what an answer. What an answer. But, you know, there's a process. Follow the process. Trust the process. And be patient with yourself. It will work. It can work. All right, well, that's the end of our problems. Not just for this quiz, but for this portion of the course, right? And so we've reached the epitome, our apex. Lots of practice using the exponential matrix in a couple of different ways. So you want to get very comfortable with that. It turns out to be a wonderful tool. And keep at it. Keep practicing. You can do this. I believe in you. You are amazing. Put in the work. Invest in yourself. Believe in yourself. You're worth taking the time to get it right. All right. Thank you once again. Hope you do well. And I hope I get to see you a little bit more.